Hello everybody, and welcome to the latest edition of the Physics Corner, a series of videos in which we set up and solve introductory physics problems. Today's episode is exactly that. We're going to show you how a physics person thinks about how to set up and solve physics problems as a general rule. Now, I'm going to show off a sample problem in order to have something to play with while we do this. It's not necessary at this stage whether you recognize or can even do the physics problem as such yet, because this is meant to be the beginning of our series. But it is going to show the thought process, the approach that we like to take when we solve physics problems, and that's its value. So let's go ahead and begin. Suppose we're driving a car heading due east at 16 meters per second, which translates to 36 miles per hour if you prefer those units. A stoplight turns red in the distance, and of course, being a conscientious citizen, you apply the brakes so that you come to a full stop in 5.0 seconds. Our questions are these. What is your average acceleration while you're applying the brakes? And how far did you travel while you were applying the brakes? Now again, at this stage, it is not totally necessary that you follow the specific physics that we have. That is something your instructors will be teaching you in the upcoming weeks. What we're interested in here is how a physics person reads a problem and thinks about how to start solving it. So that's the idea. Now, later on, once you have a little bit of experience, you can come back to this particular problem and see how we solve this in detail. But the idea right now is to follow the process. So that's what I'm going to do. I'm going to show how to solve this problem, and what I want to do after that is review where we were, what we were thinking about, what kind of steps we were taking in order to get this. Specifically, how do you get started in the first place? Let's begin. So, first thing I'm going to do is read the problem. Now, I've already done that for you, of course, but while it sounds kind of silly, this is vitally important, right? You can't understand how to solve a problem until you actually read the problem. So, step number 1, read the problem. And pay attention while you're reading the problem, okay? Step number 2, reread the problem. Now, this again is for those kinds of problems that are beyond the trivial, right? So a problem that is beyond simple. If it's something where you just plug in some numbers or give a quick yes-no answer to, then that's not as big a deal. We're interested in problems that are more complicated, that are complicated enough that you need to actually stand and think a little bit about it. So when we reread the problem, in this particular case, we're going to reread the problem for a purpose. We need to identify what it is we're trying to find. So, what are we solving for? What is it that we're trying to determine from this problem? Okay, so that will give you an awful lot of information as to what kind of problem it is and what kind of approach you're going to take. You will find out that in physics, there are many different types of problems, and there are many different types of approaches to solving these problems. And by knowing what kind of problem you're talking about, it will give you some information as to what approach you're going to take. So, for example, when we read this problem, it talks an awful lot about things like the speed that you have, the amount of time it takes to do a process. It asks questions about something called acceleration and total distance that you travel. This belongs to a class of problems called kinematics. This is a fancy word for saying how, where, when, how fast. Questions very simple like that. Kinematics is the science, or the physics, you will, of just describing how objects move. Now, different types of physics problems will be focused on different things, like why you move the way you do, for example. But that's not part of this problem. So when we read this problem, we understand that it's a kinematics problem. Even if you don't remember the term, you don't have to, you do see that it's a kind of problem asking about describing the motion. What happened to you and the car? That's all that we're concerned about. We're not concerned about why, we're concerned about what. So that's what we're kind of talking about. So we not only identify the specific items we're searching for, but the kind of problem that we're trying to tackle. Okay, so Now that we've done that, I want to go ahead and do something which I like to do. Make a table of knowns and unknowns. So a list of knowns and unknowns. And here, by the way, is where I'm going to start actually solving the problem for us while we do this. So what do we mean by knowns and unknowns? Now, sometimes you might see this as, say, given, for example, instead of knowns. I like knowns and unknowns. I think that goes together a little bit better myself. What I'm doing is I am explicitly noting what do I know about the problem, what is given to me as facts that I understand, that I have in front of me, and what are the things that I don't have. Now, the things that I have are either items that are very explicitly said or are very strongly implied. The bits that I don't know, the unknowns, are either the items that are explicitly asked about. Obviously, they're unknown if we're asking the question. Or they might be things that we don't know, but we might need to solve the problem, or could be just items we don't know about that may or may not be useful in solving the problem, but we still note that we don't have them. So, for example, since this is a motion problem, we're concerned with motion types of ideas, motion quantities, as we might say. So, what are our knowns? I read the problem. It says, I'm driving a car heading due east at 16 meters per second. That is what we may call our original or initial velocity. Now, again, if you're not aware of what a velocity specifically is at this point, if this is your very first video, don't sweat it for the moment. That's not the issue. What I'm doing here is identifying something that is given to me. That's the more important point at this stage. Later on, once you've learned a little bit about mechanics and about kinematics, then you can go back and say, oh, that's what he was talking about. So it's not necessary that you completely follow what I'm doing here in terms of the actual solution. Again, it is more about the process. So part of the process is identifying some knowns. And I'll go ahead and say that is 16 meters per second. All right. Let's also write down some other things I know. It says specifically, you apply the brakes so that you come to a full stop in 5 seconds. Oh, how much time did it take? Time, which I will abbreviate with a little letter t, is 5 seconds. That. And something that's implied. It doesn't come out and say, but it implies this very strongly. It says you come to a full stop. If you're at a full stop, that implies my final velocity at the end of this process is 0. I'm not moving. So my final velocity can be written simply as 0, like that. Okay. So those, it turns out, are the known things that are explicitly given to me in this particular problem. Okay. By the way, there are always or usually some things that are unsaid but can be assumed. For example, if you're driving on a normal street, chances are that street is perfectly level. It's horizontal. If I wanted to say that I'm driving, say, up a very steep incline or I'm taking a very sharp turn, we would explicitly say that. So we can kind of cut to the chase here sometimes a little bit. All right, what are the unknowns? Well, it specifically asks for something called average acceleration. The symbol in physics for average acceleration is a little letter A. And I'll go ahead and put a little question mark by that because it's unknown at this point. And how far did I travel? That is a change of distance, horizontal distance. And in physics, we use a symbol that looks like a little triangle and an X. This little symbol is called delta, so this is delta X. Again, don't worry if you haven't seen this yet in your classes. That's not our worry at this point. This is simply me describing how it is. All right, and that's all that I really need to know for this, or to arrange for my table here. Now, there are many other items I don't know. For example, I don't know anything about the temperature of the outside world. I don't know what the weight or mass of a car is. I don't know how many passengers you have. I don't know what the color of the car is. Very rarely are any of those types of things important. Physics questions and statements in general are usually written to be very concise. We're only going to convey the information that you need. We're not going to worry about stuff that you don't need. The color of the car is irrelevant to solving this problem. Therefore, it's not something that comes up. Now, if I have a silver car, fantastic. If I have a red car, that's also cool. If I have a yellow with green polka dots, more power to you. Irrelevant. Therefore, it's not written in the problem. Therefore, we don't have to worry about it. Okay. So I list my knowns and unknowns from the problem. This is going to give me guidance as to what I'm trying to do. Okay. Next thing, if possible, if I don't already have one, Let's make a picture. Now, before you worry about this, first off, you don't need to be anything like a great artist. I most certainly am not. None of the pictures that I'm going to sketch for you indicate that I am a fantastic artist, because again, that's not necessary. But I personally am a big believer in visuals, in being able to see what you're doing. And if I can see what I'm doing, if I have some sort of visual clues to what's going on, all the better. That helps me in my mind settle what I'm trying to figure out. So I can draw a picture that looks like this. Here's a car, like that. And that's sufficient for a car. No, don't need anything more like that. The car originally is moving with a certain velocity, like this. By the way, I'll call this in a positive direction, or if you prefer, to the east, like we typically do in a map, right? East is usually on the right-hand side of a map, so I'll draw it like that. At the beginning of the process, our van or car is traveling like that. At the end, when I get to the stoplight, my car has come to a stop. And I can just simply say this at the end if I wish. I've also traveled a certain distance, which I can, if I want to, designate in my sketch like that. So this is the distance I've traveled forward. That's the direction of the car. It's moving to the east, or I'll call that the forward direction or positive direction. And there's my car when it comes to a stop. I could draw in further things if I want to. If I want to add in, say, an arrow to represent the acceleration, for example, or if I want to put a stopwatch in to represent the time, I could do that. Not necessary. I'm not going to worry about that part of it. Okay. But the picture is going to help clarify in my head, and hopefully for you, what's happening. So when possible, and if appropriate, let's have a picture. No problem. All right, got my picture. Next step, what do I do to solve this problem? Well, I've identified my unknowns, acceleration and change of distance, or a and delta x. Physics is a subject that deals or uses math an awful lot, and there are equations or formulas that you can use to help you solve physics problems. In this particular set of problems, this particular group is a motion problem or set of motion problems, and therefore I need equations to talk about motion. It won't do me much good if I, say, have an equation that deals with, say, the thermodynamic properties of an ideal gas. I'm not worried about a gas at this point. I'm not worried about, say, the gravitational pull between the Earth and the Moon, for example, right? So I don't need those kinds of equations. I do need equations to talk about motion. So let me write down some sample equations of motion. Now, I am going to use notation that typically is used in the OpenStax series of textbooks. That's the textbooks that are most commonly used at Southern Miss. But these are also decently common symbols for things that are used at other places. And so if it's not exactly the same as, say, a textbook that you might be using, it should be close enough that we can tell the difference or be able to figure things out. So I'm going to write down what are called a series of quote-unquote equations of motion. That's in fact what they're called, in order to help me figure out what to do. Now, one thing that you should realize is that solving physics problems is actually a bit of a creative process. What I'm writing down here, these quote-unquote equations of motion, and let me jot that down for everybody so you can see what I mean in this particular example. This is like my raw building blocks, or the materials out of which I'm going to construct what I want to do. So this is my starting point math-wise. It's always a temptation, especially for beginners, to hunt and peck for the right equation, to get that one equation that's going to solve everything that you can solve for. That's usually not the greatest approach. A better mental approach is to have a series of equations as background or reference material, and then refer to them to help you solve the problem. It doesn't sound like it's much of a difference in mentality, but it is. All right, so I have my equations, which means my fifth step, now that I've done that, is find appropriate equations. And again, this is an approach that would be appropriate for an introductory physics student to take. If you're a master's student or a professor, you probably are skipping a lot of these steps because you can already kind of cut to the chase and you know the shortcuts. we're not assuming that. We're assuming you don't know the shortcuts. All right. So find the appropriate equations, and now compare your knowns and unknowns to the equations in order to select the useful equations that we can have to solve the problem, okay, or problems. If you notice in the original statement, there's actually two things we're trying to find out, which means there could be more, there's at least two separate calculations. Therefore, there's at least two separate problems within this overall larger problem that we have. Right? So let's do that as an example. All right, so I am given, again, the original velocity, the time, and the final velocity. Original velocity is v naught, or v with the 0 as a subscript, like this right there. Final velocity is vf, and time is t. One more thing to say about these equations, as we're playing with them for the first time, it may be that you can find an equation that automatically is solved for what you need. So, for example, if I'm looking for acceleration, it says, oh, acceleration equals blah, 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 blah. More often than not, that's not the case. Rather, you're going to find that an equation is got your item that you're interested in buried inside of it, and you're going to have to do some algebra manipulation to get what you want. So it's not a guarantee that it'll have a solution for acceleration. And if you look, none of these are solved directly for acceleration. So what do I do? Okay. Next step, so I compare my knowns and unknowns to select useful equations. So I go through the equations. And again, for illustration purposes today, let me rewrite these so we can play with them directly. Okay, so here's my first equation. So, do I know the distance that we travel? No, I don't. That's one of the questions, as a matter of fact. Do I know the original velocity? Yes, I do. I can check that off my list. Do I know how much time it's going to take to slow down? Yes, I do. T shows up in two places, here and here. Do I know the acceleration? No, I don't. So if we look at this first equation, I've encountered something of interest. I have two unknowns in one equation. If you remember from algebra, that can give me some relationships, but it cannot let me solve for anything specifically. I can't solve for acceleration and get an actual number if I have another unknown in the equation. So I need an equation that has just one unknown in it. So can't use this one, at least not yet. Now, it turns out maybe we can come back later on and use it, perhaps. But for the moment, we can't. So let's move on to a different equation. So this one's no good. All right. Let's try the next one in the list and take a look at it. So VF equals V naught plus AT, like that. And let's go through the same mental process. In my known quantities, do I know the final velocity? Yes, I do. Do I know the original velocity? Again, yes, I do. Do I know the acceleration? No, it's an unknown. Do I know the time? Yes, I do. And check it out. Now I have an equation that has lots of known quantities and only one unknown. And that means I have something I can solve for. So this equation I can solve for. Now, again, notice it's not solved already for acceleration. I'm going to need to do some manipulation to get my answer. That's the next step. But now that I've identified a useful equation, I can use it. So use algebra if necessary. Well, sometimes I may have the solution already, but use my algebra if needed to solve for an unknown. So let's do this carefully here. Rewrite my equation that I'm going to play with. Now I'm trying to isolate A by itself, right? So first things first, subtract V naught from both sides. So VF minus V naught equals V naught plus AT minus V naught. The reason to do this is because V naught minus V naught is 0. That disappears. And it leaves me with VF minus V naught equals AT. So first algebra step, I've gotten all the stuff I can moved over to the other side. Second thing is, it's not just A, it's A multiplied by T, or acceleration multiplied by time. I need to divide everybody by time. So let's do that. So let's divide both sides by time. So what will happen on this side, I'll get this as a result. On this side, time divided by time cancels. And again, I'll have these gone. And so in the first step, I subtracted V0 to move that over to the other side. In the second step, I've divided by time to eliminate that. And again, move it over to the other side. And now I can rewrite it like this, acceleration. And by the way, I could keep it on the right-hand side, but let's just move it to the left. It looks easier, more common to do that, is equal to Vf minus V0 divided by t. So that is my algebraic solution. It is not a number solution yet. It's an algebra solution. Now, physics people like to do this. It's very common, it's very understandable even, for students to want actual numbers. And we'll give you a number in just a moment. But for a physics person solving a problem, this is a little bit better and more fundamental thing to do, because I've got a solution that works for all sets of numbers, lots of numbers, not just the numbers in my particular problem. If I gave you a different set of numbers, I could still go back and solve for it. I could still find those numbers with this. So that's what I'm doing here. Now let's plug in some numbers. Once you have your algebra solution, plug in some numbers. Notice that plugging in numbers is really far down the list of what we're actually doing. So, acceleration equals, what's my final velocity? 0. What was my initial velocity? 16 meters per second. How much time did this process take? 5 seconds. So 0 minus 16 is a negative 16. Negative 16 divided by 5 is a negative 3.2. My units, meters divided by seconds twice. So meters per second squared. And this is my answer. Okay. So that's one of my answers. I'm going to give you the other one in just a moment. So that's how I found out acceleration. Okay. Notice what I did. I put in the numbers nearly towards the very end of the process, right? We did an awful lot of work ahead of time before we got to this stage. Now, in some cases, it may be more to your advantage to put the numbers in earlier. I could think of a few examples, for example, from electricity. Electrical circuits are famous for being good for that. But as a general idea, usually you have a lot of steps to do before you actually put the numbers in. And this is a good example of that. Okay. So, with that number then, now I can go back and look at my other equations and see, can I find another set of equations perhaps to use to my advantage, right? So let's continue onward. This next step is apply again to any other unknowns. And we have another unknown, that was delta x. Now, just to cut to the chase, I'm going to do it this way. I have an equation up here that looks like this. Delta x equals 1/2 v0 plus vf multiplied by t, like that. Okay. And just to be on the safe side, let's double check, see if this will be useful for us. 1/2 is just a number. This is what I'm trying to find. V0, that's a known. Vf is a known. T is a known. So I do have everything I need to solve this problem. So let's go do that. So let's now plug in the numbers. So again, it says apply again. So repeat the previous couple of steps, but now for a different quantity. V0 was 16 meters per second. Final velocity was 0. Now, some people, if you want to, you could put the units on there as 0 meters per second, but 0 multiplied by anything is 0, so it doesn't matter. Leave that alone. And 5 seconds there. All right, so let's see here. 16 plus 0 is 16, of course. 16 divided by 2 is 8. 8 times 5 is 40. And my answer numerically is 40. If you look at the units, meters per second here, cancels the seconds there, and I get meters here. And there's my answer for delta x, 40 meters. All right. Now, we've got our answers. That is done. The problem is done. What I want to do here is a couple of last comments to sort of double check our results and comment on some things. So last step is, or another step we can do is to check the units. Now we have a different video talking about units already, so I'm not going to repeat all of that right now. But what I can do is say, hey, let's see if the units make sense. So, for example, we solved for acceleration. Now again, we already realized that you may not be at this stage yet in your classes, so you're going to have to trust me on this one, but the standard units for acceleration are meters per second squared. When we did our calculation, we got meters per second squared. Okay, so the units are good. How about for the distance? Distance, delta x is a kind of a distance. It came in meters. Yeah, okay. The units all make sense. Now that doesn't guarantee your numbers are correct, but it's certainly a hint that they're in the right direction. Okay, so that's good. All right, so we check the units. Units are good. All right. Now, other things you can do. I would check to see if it makes physical sense. So check if your solution, or solutions, plural, make sense. Now, you may or may not be familiar with all the units we're using, but again, that's something that'll come with practice. But let's take a look. 40 meters. 40 meters, a meter is a little bit more than a yard. So this wouldn't be too far off to say we're just over 40 yards. Is that the kind of distance that you would travel if you put on your brakes? You say you're traveling around 35, 36 miles per hour, and you put on your brakes for several seconds. Would you go forward some 40 yards or so? That sounds like a reasonable distance. Think of it this way. We didn't find, say, 40 millimeters, and we didn't find 40 light years, right? We found 40 meters. That's a reasonable amount of distance that you can imagine traveling. So if it's not the perfectly correct answer, it's certainly in the right ballpark. It's on the right lines. Now, the acceleration is a little bit tougher to talk about, but I do want to take a look at one aspect of the acceleration. So let me bring back the paper briefly, real quick. Notice it has a negative sign on it. What does that mean? In this particular case, what's happening is that we're slowing down. Now, negative acceleration doesn't necessarily mean slowing down, but it does mean this. We were going to the east or forward. What the change of velocity or the acceleration did was to slow us down or to act in the opposite direction. Okay, now think of it this way. If I wanted to speed up, I've used a whole different pedal, right? I've used the gas or accelerator pedal, and that would have sped me up in the same direction I was already traveling. Brakes act to change your speed in the opposite of the direction you're currently traveling. And lo and behold, there's a negative sign that indicates that. So while the number 3.2 meters per second squared might not be familiar to you quite yet, it will be soon enough in time. But even if that's not something that hints a lot to you, the sign certainly does. We expect that we'll be slowing down, and so we are. So, to recap very quickly, when you do a physics problem, first, read the problem. Second, reread the problem, but now identify what kind of problem are you addressing. Is this a motion problem? Does it have to deal with forces, energies, electricity, gases? There's all light, all sorts of different kinds of things, but what kind of problem is it? Now, usually because you're in a particular chapter, part of your study in class, you'll know, but still, it's worth to identify what type of problem you're trying to solve in the first place, right? Now, once you've done that, you can go ahead and identify the specific things that you know and don't know about the problem. What are the facts that you're given or can figure out? What are some facts that you're trying to find out or you don't have but might be useful to know? If it's possible to sketch a picture, draw a small, simple picture to illustrate what's happening. I like to do that myself because I think it helps me clarify what's happening, right? Once I have my picture in mind and I've got all my ideas of what the knowns and unknowns are, what kind of problem I'm dealing with, then if I don't know them off the top of my head, I can consult my textbook or my notes and find equations that have something to do with the problem. If they don't, search for other equations, right? So once I find my equations, I can go through the equations and identify which equations make sense to use given the knowns and unknowns that I have. At the very tail end of the process is when I plug in my numbers. Once I have plugged in my numbers and I've calculated a result, I check my units to make sure the units agree, so I have the correct kind of units in my quantities, and I check to see if my solution makes physical sense. If the numbers I'm getting actually have something to do with what I expect I should get. And that is a good strategy, general strategy, for solving physics problems. Thank you, everybody, for your attention. Technical assistance for this series is from Sidney Geltraw and Sophia Turner. Funding is from the University of Mississippi and the University of Southern Mississippi. These videos are recorded in Hattiesburg, Mississippi itself. I am your host, Dr. Christopher Sorolla, thanking you again for your attention, and clear skies, everybody.